this is Mrs. Boyd, and today we are going to do some molecular analysis for our intermolecular forces lab. So let's just kind of run through what molecular analysis involves. So we are going to write compound names and chemical formulas, draw molecular structures and 3D structures as needed, calculate the electronegativity differences for each bond and write those numbers above the bond, highlight polar bonds blue and nonpolar bonds yellow, draw in bond dipoles, and identify the bond type. Finally, we're going to do a carbon count if necessary. So let's go ahead and get started. The two molecules I'm going to be comparing are hydrogen peroxide and acetaldehyde. And hydrogen peroxide has a formula of H2O2. And you can see that I have bonded all of my atoms together. And I also wrote down the electronegativities. So oxygen has 3.5, hydrogen 2.1. So once I have that, then we're going to go ahead and see if we can identify where the electronegativity differences are and if we have any polar bonds in our molecule. So let's go ahead and begin right here. We have an electronegativity difference between oxygen and hydrogen, and that is going to be 1.4. So that is going to have a dipole arrow. So we're just going to go ahead and draw that in right here. And it is considered a polar bond. We also have this oxygen here. However, that electronegativity difference is 0. So we are not going to be putting any polar bond there. Instead, that is going to be a nonpolar bond. And finally, between oxygen and hydrogen, well, we already calculated that, and we know that we have another polar bond. So we will highlight that right there. So it looks like we have two polar bonds, and let me add this other dipole arrow. And of course, dipole arrows are always drawn towards the element that is more tightly holding onto the electrons, and in this case, that would be oxygen. We call that our polar bear, and of course, hydrogen is our penguin. So we have a part of the molecule that is negatively charged right in this area and over here as well. And then we have some portions of our molecule that are positively charged. And so for sure you can see that there's going to be some attraction going on in hydrogen peroxide with neighboring hydrogen peroxide molecules. So let's go ahead now and take a look at the bond types that we have here. So here are our choices over here. We have all these different choices, and we are going to decide which one or which couple we have. So first, of course, we have to automatically assume there is London dispersion because every molecule has that. So we will highlight London dispersion. Then we want to take a look at those dipole arrows, and do we have a hydrogen that is attached to either a fluorine, an oxygen, or a nitrogen? And yes, we do. We have a hydrogen right here that is bonded to an oxygen. So we can then assume that we also have hydrogen bonding. And matter of fact, let's go ahead and write down how many H bonds we have, and that number would be 2. Finally, we want to see if we have any dipole interactions, which would be if we don't have a hydrogen bond, but we have instead electronegativity differences between other atoms that are not hydrogen. And in this molecule, there are not any, and we also do not have an ion. All right, so it looks like we have a molecule with 2 hydrogen bonds and some London dispersion forces. All right, let's apply the same kind of analysis to acetaldehyde, CH3CHO. And once again, you see that I have built our molecule here. So let's go ahead and just jump right into our dipole arrows. So let's see if we have any bonds here that are polar. It looks like between carbon and oxygen we have a difference of 1 because it's 3.5 minus 2.5. So we have a dipole arrow right here, being electrons being pulled towards oxygen. And it looks like all of the rest are actually non-polar because their electronegativity difference is lower 0.4 or lower. So we have all of these carbon-hydrogen bonds are all non-polar bonds. So this molecule is kind of interesting because it has a bit of a side over here that kind of tends to be a little bit non-polar, and then we have a side right here that definitely tends to have more polarity to it. So let's see if we can identify what bond types we have here. Okay, so let's go ahead and start with London dispersion. Always start with that. We have London dispersion in every molecule. Right below ion, do we have any ionic bonds? No, everything is covalently bonded. Then we're going to be looking for any hydrogens bonded to F, O, or N. And we have hydrogens, but they are bonded to carbons, so we do not have any H bonding. And so that's going to leave that dipole bond, this one right here, as the bond type that we have. So we have a dipole, and we have one. Okay. So now that our molecular analysis is done, we've kind of torn apart the molecules, we've kind of analyzed like where can they be attracting other similar molecules. Now we have to really think to ourselves, all right, which one of these, and they're both clear liquids by the way, which one of these is going to boil first? So let's take a look down here at our how to compare chart. So this is the order of importance. So anytime we have any kind of bonds, we always want to take a look at ionic bonds first. So we can just cross that one off. We can skip it. We have no ionic bonds. The next is the molecule with the strongest intermolecular force. And in this case, we know that there are 2 hydrogen bonds up in hydrogen peroxide, and none in acetaldehyde. And we know that hydrogen bonds are stronger than dipole-dipole. And they are also going to be stronger than London dispersion forces. So far, H2O2 is going to win that battle. Let's continue with a little bit more analysis. So the next question is the most polar bond. So this requires actually looking at the electronegativity differences. And it looks like in acetaldehyde we have a difference right here of 1, an electronegativity difference of 1. And then we have here an electronegativity difference of 1.4. So 1.4 at both of our hydrogen bonds. So it looks like even in the second category, the most polar bond, we also have H2O2 is also our winner. We can continue, if we don't have a clear winner, a few of these in, then we can keep going until we find some breaking point where one molecule seems to win out over the other. We are going to go ahead and stop here for now. Let me just mention these others really briefly. The largest number of polar bonds, this could be an important factor here. We also have polar groups at the end of the molecule versus in the center of the molecule. That could also affect boiling point. And finally, last but not least, if everything else is even, we can count the number of carbon atoms, because in that very last case, the larger molecule is going to be more difficult to boil. So what does this mean? So we have H2O2, and I said earlier it was kind of winning. It has the strongest intermolecular force and the most polar bond. So what that means is that hydrogen peroxide is going to be predictably the molecule that has the higher boiling point. And that is because it has stronger forces in between neighboring hydrogen peroxide atoms than acetaldehyde does. So our guess, if we were going to hypothesize, would be that if we boil these two, we would have acetaldehyde have a lower boiling point. It's going to break apart from its neighboring molecules much sooner than hydrogen peroxide would. So let's go over into the lab and see if that actually proves to be true.